Okay, welcome everyone. Today again is, after looking at the quiz, is going to be all about infinity. So that's the plan, and negative infinity. They kind of go together. So let's take a look at the quiz. Okay, so here's the quiz, and two different problems, same idea but different. And that is, we need to first look at this graph. And part A is determine the intervals where f prime of x is greater than 0. And what I kind of anticipated is eyeballing it. Again, you're not supposed to come up with the equation of the function or anything like that. This is just understanding what it means for f prime to be positive. So what's the first? There's a couple intervals. What's the first interval where f prime of x is greater than 0? And yeah, negative infinity to negative 1. And by the way, that's fine. I'll also accept, say, negative 2.5 to negative 1, because again, you can't see the whole graph. You can never see the whole graph when there's an infinity involved, because that's not possible. But so I would accept it as long as it's negative, something past negative 2 to negative 1. So how about negative 2.5? I'm going to, easier to type. So negative 2.5 comma negative 1. And, all right, so we just did that. And notice again, f prime of x is greater than infinity when we're moving up, when we go from left to right. Okay, that's how you kind of look at it as a graph. So after negative 1, then we go down. So then after that, when do we go off to when do we go up again? For what interval?
We start going up at 2.
Mm-hmm.
And so that would be positive 2 to positive infinity.
Exactly. 2, comma, and again, infinity, I'm going to say 3.8. Because after that, we really can't see. I wouldn't take off points for not being able to see it, because it could go down at 12 for all we know. But it turns out the function I put in a Desmos actually does go up to infinity. Okay, all the way as we go to infinity. It was some cubic, I think. Okay, any questions on part A? Again, it's just an eyeball thing. Not even fancy typing. Okay, then determine the intervals where f of x is decreasing. And I decided to do B to look different than A, because I wanted you to understand both ways of thinking about it. One is the derivative is greater than 0 is increasing. In terms of calculus, in terms of derivatives, if f is decreasing, what do you know about f prime? So if f is decreasing, huh?
F prime would be negative if it's decreasing.
Exactly. So it's just the same. It's just different words for saying the same thing, basically, because we had a theorem that they're the same. So now in this case, there's only one interval that we can see where it's decreasing, and that's kind of negative 1 to 2, because that's the only thing left. Okay. And because I didn't say the word strictly, I don't think I take off points for this, but it's good for you to understand the language. If you don't say strictly, then if it's flat, it still counts. So that's why I put square brackets around all of these intervals. Whereas if I said strictly decreasing, you would put round brackets to not include negative 1 and 2. Okay, I don't think I'm going to be that picky, but it's important for me to tell you that this is how the language works. Any questions on that? Okay, now we got to determine the inflection point or points for this function. And how do we find the inflection point or points? Again, it's for the second derivative equals 0, but graphically, what are we looking for? About curves. What about curves, though? We're definitely looking at the curve.
Isn't it like when the graph switches from concave down to concave up?
Exactly. It's when the graph switches from concave down to concave up, or vice versa. Also, when it is the steepest. Okay. And steepest means we're going down and then we're going up. So let's look at, so first thing over here to the far left, there's really not a point of inflection at all. Okay. It just gets less steep, less steep, less steep. It's just concave down, concave down, concave down. But then notice that it's concave down over here on the left, but then on the right, it's concave up. So where is the switching point approximately? What can you
Around
tell me?
0.5.
Yeah, it looks like about 0.5. So I'm going to try x equals 0.5. Okay. If you said 0.6 or 0.4, that's fine. But if you said 2, that's not okay. Any questions? Any questions on this? Okay. No questions? Okay, again, concavity is important. It's hard to explain, why it's so important, but it really is. I'm looking through my list of people here. I'm not seeing my prior stats students. Any of you had stats before? Just because you weren't my student doesn't mean you haven't had it. Okay. It turns out that concavity is important for stats, and in particular for the normal curve. You've probably all heard of a bell curve or normal curve. Turns out that the inflection point is where the standard deviation is, where the z-score is 1, or you have 1 for the standard normal curve, and -1. So it just happens to be that. The proof is a little messy. I'm not going to do that, but just let you know, it even comes up in stats. Okay, now, of course, when I teach stats, I don't talk about it because they haven't had calculus yet. Okay, so that was part C. Part D, where is the graph concave up? So where is it concave up? So remember, concave up visually is, if you think of it raining or snowing, probably rain, let's go raining. And which by the way, might happen in the next few hours. Not quite yet, but we're actually changing seasons today. So today is a point of inflection for the weather. Okay. And where is it concave up? Okay, x equals 2. X equals 2 is a point at which it's concave up. Okay, but not just, but 2.1 is also concave up. Because if the rain happened, it would all fill up. And the idea here is it goes from the inflection point, and the inflection point, not 0, okay, because we decided the inflection point was 0.5. So 0.5 is a change of concavity. So it's going to go from 0.5 off to infinity, or 3.8, I'll use that. Any questions on that? And the way I'm going to grade it, by the way, is this left-hand endpoint needs to match with your inflection point, because that's a change of concavity. To the left of 0.5, it's concave down. To the right, it's concave up, if we've called that the inflection point. Any questions on that? Okay, so if you had 0.4 for inflection point, then you need to have 0.4 on your left bound. Any questions at all on the first question of the quiz? Okay, again, it's a lot of questions, but they don't take long. It's just looking at it and writing down the answer. Okay. Whereas the next one doesn't even have A, B, C. Here, we have to do one thing, and that is use the second derivative test to locate and classify relative extrema. But this, we actually do stuff. So if we want to use a second derivative test, then what's the very first thing we have to do? It should be obvious.
Take the first derivative.
Yeah, you got to take the first derivative. Okay, and you have to take the first derivative, obviously, to take the second derivative. But yeah, even with the second derivative test, the first derivative test is important. So let's do that. So we have f of x is sine of x plus cosine x. Okay, and I expect you all to be able to take that derivative without any stress. What's the derivative of the sine of x?
Cosine of x.
Cosine of x. So I got my cosine x. What's the derivative of cosine x?
Negative sine x.
Negative sine of x. So just so I can type less, I'm going to put the negative sine of x first because it's easier to type. All right, now before we even get to the second derivative test, we need to locate the possible relative extrema. And to locate the possible relative extrema, what are we doing with this derivative?
You take the derivative and equal it out to 0.
Yeah, we set it equals 0. And yeah, you are responsible for knowing very basic trig. So I'm going to set negative sine of x plus cosine x equals 0. That's the same thing as sine of x equals cosine x. Or maybe I'll write cosine x equals sine of x. Any questions so far? Okay, where are the sine and cosine the same? What angles? And yeah, you are responsible for knowing that.
Pi divided by 4.
Pi over 4 is one of those. And I specifically
And
said
5
between
pi
0
over
and
4.
2 pi. So we have pi over 4, and what's the other one?
5 pi over 4.
5 pi over 4. So we get pi over 4. And we also get 5 pi over 4. And those are the only two at which sine and cosine are equal in between 0 and 2 pi. Any questions on that? Maybe I'll write x equal. And let's do the following. These are the critical points. And by the way, hopefully you know this, sine and cosine are very differentiable. So you don't have to worry about points of non-differentiability at all. So now we need to use a second derivative test to classify them, because right now we don't know which is a max, which is a min, or maybe neither. So let's go classify them. So if we want to use a second derivative test, this is a really easy question. What do you think we need to do next?
Take the second derivative.
Take the second derivative. It wasn't a trick question. So we need to find f double prime. And actually, I think I didn't write prime there. That was f prime. Let's find f double prime, which is pretty easy. So we want f double prime of x. So what's the derivative of negative sine of x? Right, negative cosine x. And what's the derivative of cosine x?
Negative sine x.
Negative sine of x. So we just get negative sine of x minus cosine x. All right, so we're using the second derivative test, which means we need to plug in pi over 4, and we need to plug in 5 pi over 4. So let's do that. So I'll start with pi over 4. So f of pi over 4 is equal to negative sine of pi over 4. Minus cosine of pi over 4. That didn't work. And I don't even care about what the number is. I care about whether it's positive or negative or 0. And remember, pi over 4 is in quadrant 1. Sine and cosine in quadrant 1 are both positive. So what can you say about negative sine pi over 4 and negative minus cosine pi over 4 in terms of the sign, S-I-G-N? So what can you say? Is it positive, negative, or 0? Shouldn't even need a calculator.
Negative square root 2.
Yeah, you don't need a, I don't even want a number. I want positive, negative, or 0. That's all I care about.
Negative.
It's negative because we're in quadrant 1, sine is positive, cosine's positive, so we get negative minus a positive, and that's just a negative number. Don't need a calculator or anything. All right, so now we can use the second derivative test and make our conclusion about the x equal pi over 4 being a max or a min, or we don't know. So what can we say? So at x equal pi over 4, the function has a relative. Now, if the second derivative is negative, what does that tell you? Max, min, or neither?
It's max.
Maximum. Any questions on that? Okay, now I do the same thing, and I'm going to copy and paste and change because it's a lot faster to type. So let's start out with f double prime of negative pi over 4. I just throw negatives everywhere. Sorry, not negative 5 pi over 4, it's 5 pi over 4. And I throw 5s everywhere. So now we're in quadrant 3. So in quadrant 3, the sine and cosine are both negative, right? So if you have negative the sine minus the cosine and sine are both negative, what does that tell you about being positive or negative or 0? It's positive. So we know that f double prime at 5 pi over 4 is positive. So now at x equals 5 pi over 4, the function has a relative. Well, if you're positive, you have a minimum. Any questions on this quiz? And I want to emphasize I did not need a calculator. Okay. The idea is I try to make the numbers nice. Now, of course, you have to remember basic trig, but nothing too advanced, just pi over 4 and 5 pi over 4. And quadrant 1, quadrant 3. So an inflection point is when the second derivative or goes from positive to negative or negative to positive. Another way of saying it is that an inflection point is a point at which from left to right, it changes concavity. Does that help, Alexi? So an inflection point means that the concavity changes. Yeah. And so that's the visual way. And then the calculus way is that the second derivative changes sign as it passes through that point. Any other questions? Very good question. Very important.
Yeah, Larry, I'm still confused on f double prime of 5 pi over 4. Is it because like if you actually do sine 5 pi over 4, you get negative square root 2 over 2, but then there's two negatives, so that makes it a positive? Is that why we got a positive answer?
Yeah, you could do, I mean, like I said, you can do the full calculation, but I'm trying to show you
Yeah.
the easy way. The easy way is that we're in quadrant 3. Quadrant 3, sine and cosine are both negative. Do you know that?
Mhm.
So if sine and cosine are both negative, then negative sine and negative cosine are both positive. Is that right? Is that clear?
I'm sorry, I'm just not following. Like
Okay, so if you take
because
negative a negative number, you get a positive number, right?
yes, yeah.
So we know that the sign is negative, so negative sign is positive.
Okay.
And
Yeah,
similarly,
okay.
the cosine is negative, so negative cosine is positive.
Okay,
So I'm just adding two positive numbers, and that's greater than 0.
that's correct. Okay. Okay,
Yeah.
thank you.
And then you don't have to remember every little detail of the trig, but I do want you to know that, you know, in the quadrants, when are the sine and cosine positive or negative? That's actually really important. And one way to remember it is the sine is the y coordinate, and y is negative in quadrant 3, and the cosine is the x coordinate, and x is negative in quadrant 3 also. Do you see that? So there's lots of ways of visualizing.
Okay.
Okay, good questions. Like I said, real important you ask questions. Other questions? Okay, let's go to our day's stuff. And by the way, we have a whole lot of things to do. Unlike like related rates, we only had one item, I think, after Q&A. Should you be afraid because there's a lot of things? What do you think? No, it's the opposite. The more things, the easier the day. Okay, that's what that means. If you have one thing, that means it's brutal. So just let you know that. So this is not a hard day. Okay, so we can relax a bit. Okay, there's still stuff to do. So what we want to do is we want to talk about limits. And let me ask, are there any questions about anything in general? And while you're thinking about it, again, if you can say a question, that's fine. If you want to type something, that's fine. Just want to let you know what I've been doing the past week or so. And I think I got 2 more days. And that is I am redoing all of the videos because they were done originally. I did it, you know, years ago in Flash, and that doesn't work anymore. So there's a playlist now that I'd say I got a couple more days, maybe tomorrow actually. I'll finish, and they'll be full example videos of everything we do. And that should help you in kind of studying and practicing and seeing good examples. Okay, it's a real pain to move it from Flash to YouTube because Flash doesn't work anymore. So that's why I've been doing this. And I have 1 more month and the whole thing just is a disaster and everything closes on Flash. So just let you know, that will appear this weekend, probably in the syllabus, is that there'll be probably over 100 videos of different examples that you can watch. Okay, including everything we do in this class, just about. So that's just a note, and they're about 4 minutes each. Somewhere between 2 and 7 minutes, I should say. Okay, any questions? Okay, let me talk about number 3, and it's a little weird because, you know, it's in the book and I'm trying to, you know, try to go through the book in terms of the order, but the book literally just repeats itself. We actually did number 3. You got a question, Ma? No, sorry. You want to join a partner, maybe. Join a project group or a presentation group. So number 3 is is the limit as x goes to a of f of x equals infinity or negative infinity. And what do we call that again in 2 words? I mentioned it in our intro, 5-minute intro. If you have that limit, then what do we say you have in 2 words? You can even use initials if you want. Yeah, that's a vertical asymptote. Okay, so you have a vertical asymptote if the limit as x approaches a of f of x equals equals infinity, or if it equals negative infinity. And I thought I'd just show you some pictures. I think that's the easy way to see it. Desmos is good for that. The most classic one is if we look at, let's say 1 over x squared. So that certainly has a vertical asymptote. And if you let x approaches 0, notice you get 1 over 0. And 1 over 0 squared, it means positive. So that's why it's positive infinity from left and right, by the way. So I want to remind you, technically, the limit does not exist at 0, but the limit is infinity. And the reason why why is that not a contradiction? To say the limit doesn't exist, but the limit's infinity. Well, that sounds like it exists. What's wrong? Why is that okay, mathematically? Any thoughts? Don't see y'all jumping in. Okay, the idea is infinity doesn't exist. Okay, if you ever think that you're going to get an infinite amount of money, you're wrong. Can't happen. So infinity doesn't exist either, but it's a special not exist, and that's why we'll use infinity or negative infinity instead of just saying DNE. Okay, whereas there's other times when it doesn't exist and it's not infinity or negative infinity. So this is an example of a vertical asymptote, and you can also have one that goes down, negative 1 over x squared, and you can see that goes down to negative infinity, left and right. You could also have a vertical asymptote where it might switch, whether you're going left or right, and it's still a vertical asymptote. And then we're going to have a left-hand limit being a negative infinity and the right-hand limit being positive infinity if you're looking at 1 over x. That's the idea of vertical asymptotes. They don't have to happen at 0. They can say happen at 1. So there's an example of a vertical asymptote that happens at 1 over x minus 1. And that, when you get close to 1, you go off to infinity or negative infinity. Any questions on this idea of vertical asymptotes? Okay, the number 1, absolutely number 1, and there isn't even a good number 2. I'd say there might be a number 10 after that. Examples of vertical asymptote is when you have a 0 in the denominator and not the numerator especially. Okay, so if you have a constant, non-zero constant over 0, that's going to get you a vertical asymptote. And by the way, you may say, well, what about the tangent of x? That has a vertical asymptote. But why does the tangent of x have a 0 in the denominator? So if I type in tangent x, definitely have a bunch of vertical asymptotes. But why is there a 0 in the denominator? It's kind of hidden. Why can I say that even though I don't even see a denominator? Any ideas? I don't see y'all jumping in. How do you define tangent of x? When you first learn it in your trig class. Yeah, sine over cosine. So there's a denominator there. It's just hidden. And when the denominator is 0, when cosine is 0, you get a vertical asymptote. So that's why tangent of x has a vertical asymptote. So does secant, so does cosecant, so does cotangent. Okay, so those all have denominators that give you 0. Can you think of a function that has a vertical asymptote where it doesn't have a denominator no matter how you look at it. And the hint is it's an important one. It's not some weird function that you've never seen before. You'd have to think a lot. We even spent like a whole day on it in this class. Can you think of a function that has a vertical asymptote that doesn't come from a denominator at all? A to the x. So if a to the x doesn't have a vertical asymptote, like 2 to the x has a horizontal asymptote, but there's no vertical asymptote on a to the x. But good try. Yeah, logs. Okay, so if I type in ln of x, then we get a vertical asymptote. And notice, sometimes we'll say this is a right-only vertical asymptote, because on the right, you get the vertical asymptote. Okay, so ln of x is the other one. Okay, that's pretty much the only ones that you've seen that have vertical asymptotes. You can either have a denominator, even as a hidden denominator, being 0, or you could have ln. Notice if you have a to the x, like 2 to the x, it may look like you have a vertical asymptote, but why don't we? So if you think it has a vertical asymptote, because it does go way up, right? Then tell me what number it has a vertical asymptote at, and I will tell you that can't be true because we don't get to infinity when we approach that number. Do you see that? Okay, so when you're looking at Desmos, it might look like it, at x equals 4, there might be a vertical asymptote, but 2 to the 4th is just 16. And a little past that is not near infinity, and a little to the left is not near infinity. Do you see that? So 2 to the x, for example, does not have a vertical asymptote. So just because it's steep doesn't mean it's a vertical asymptote. It literally has to go to infinity. Any questions on this idea? Okay, so then so again, I'm not going to spend that much time on this because we already had a day on this. But what I do want to talk about is the next place where you'll see an infinity, and that is the limit as x approaches infinity of f of x. So now we're saying let x go off to infinity. Okay, in the real world, why do you care? When do you care about that? When is that? There are a lot of applications. And where are they? Where do you see that in the real world? Okay, so, and the real world could be in other classes that you take that aren't math classes. Any thoughts? I don't see y'all jumping in. Extrapolating data. Not sure what you mean by that. Not sure if I see a x goes to infinity, maybe. Like predicting. Okay, there's some kind of predicting, but let me put some words into that. Long-term predictions. So what's going to happen in the long run? Sometimes you'll say long run, and that really means x goes to infinity. Maybe that's what you meant. Okay, not predicting what happens tomorrow, because that's x goes to 1. Does that make sense? So it's really in the long term. So if you want to predict what's going to happen in the long term, then we're going to take a limit as x go infinity. So for example, do you think we have a limiting population on Earth of people? Do you think that's true? Or do you think we're going to go off to, do you think we'll be off to infinity? Or do you think we'll never hit a limit? We're just going to go up and down forever? But do you think we're going to have an approximate limiting population? What do you think? And again, this isn't a math question. Okay, and the answer is yes. Okay, so let me tell you something. The first thing is, if you consider infinity being like a few hundred years, then the answer is that we think that there's going to be a limiting population. We don't know exactly what it's going to be, but they're thinking around like 15 billion or so. Again, there's lots of models. But then in the very long term, what's the limiting population of the population of humans? No question about it. It might make you cry. Yeah, 0. So the bad news is in 1 trillion years from now, there won't be a universe anymore. It's really hard for people to live when there's no universe. There'll be no molecules left in the universe, just let you know that. It's kind of a bummer, but we'll all be dead, so it doesn't matter. So that would be another example of a limit as x goes to infinity. How about in chemistry? What do you call it in one word? Starts with an E.
Entropy.
Huh?
Is it entropy?
No, not entropy, actually. Entropy tells you how disordered things are. Right? What is that? Someone tried to talk, I didn't hear it. Enthalpy? Okay. No, they're kind of similar. There's entropy and enthalpy. One's how disordered, the other's how much energy. Maybe I said it wrong. Maybe entropy is the energy and enthalpy is the disorder. I always get them mixed up.
No, you have it right.
I did have it right. Okay. Yeah. I often second guess myself. Okay. Okay. Equilibrium. Equilibrium. In chemistry, you have to do equilibrium a lot, don't you? Right? If you put a couple chemicals together and you let's say, what is equilibrium? That means what happens as x goes to infinity, as time goes to infinity, as you watch this reaction go. Does that make sense? And that's equilibrium. And they often call it equilibrium in biology, also in ecology, because you want to say, well, what happens as time goes off to quote unquote infinity? It's not really infinity, but maybe 20 years or something, and to see what's going to be the equilibrium. Okay. Yeah, equilibrium never happens, but infinity isn't a number. So that's okay. It's okay. Again, this is math. In math, you can say whatever you want to say, even if it never happens, but it's useful. And that's what matters more, is that it's useful. Does that make sense? Okay, so very important to talk about equilibrium. Equilibrium is a big piece of science. So what's going to happen over the long term? And that's when x goes to infinity. Okay, and again, time is probably the most common that you'll see, is what happens when the time goes to infinity. Okay, and they don't really mean infinity, but they kind of have that idea. Okay, so now I want to look at the formal definition quickly. So I want to remind you, this is a formal definition of the limit when you don't have infinities. And that is the limit as x goes to c of f of x equals L means that let epsilon be greater than 0, then there exists a delta greater than 0, such that if x minus c is less than delta, then absolute value of f of x minus L is less than epsilon. Do you remember that happening a while back? I think it was week 2. Or you want to keep it out of your brain because it was so scary. I'm not sure, but it definitely happened. So we want to take this and we want to adjust it. Okay, this was just the general definition of a limit when you don't have to worry about infinity. So I'm going to copy and paste. And now let's pop in, instead of L, let's put infinity. I think it's that one. Yep. Okay, so now we want to say we're heading off to infinity. So if you're heading off to infinity, that means that you're going to be bigger than anything when you get to be long time. Does that make sense? When you get to close to C. So now we're not really looking at epsilon greater than 0 because you're not close to infinity. That makes no sense. Do you agree? You can't be close to infinity. But what you can say is you're bigger than any number that you can imagine. So instead of let epsilon be greater than 0, what I'm going to do is I'm going to say let capital N, sometimes I use N, sometimes I use M, be, and I'm going to do a double greater than 0. Have you seen that before?
Nope.
Okay, what that means is much greater than 0. You've now seen it. Okay. And it's nice notation because it kind of, when you see it and you hear it, it makes sense, doesn't it? That would be a good thing to use for much greater. Greater than 0. Okay. And that's standard, by the way. This isn't me getting weird. So now we're going to let's start with a really big number. Then there exists a delta because we still want to be really close to C, such that if x minus c is less than delta, then, well, you're not trying to subtract infinity. We just want f to be big, right? And we don't even need absolute values because f is positive if we're close to infinity. So we're just going to have f of x. Oops. Won't let me do it. Let's try again. All right, let's just do it. Oh, I see. It's on the other side. So we're just going to have f of x. So f of x is greater than n. So it says that if somebody gives you an n, then you could say, well, I can get really close to C so that no matter where you are in my little close to C interval, you're going to be bigger than n when you apply the function. And that's what it means for the limit to be infinity. And just to note, because it's very easy to do it typing wise when you have copy and paste, is that if we want to go to negative infinity, then we have an n much less than 0. And then we want to make sure that f of x is less than n. So nothing really changes. Just got to be on the other side. Any questions at all on the definition of the formal definition of the limit going to infinity? It just means that if someone throws a number at you, you can get bigger than that number in some small interval near C. Okay, next thing I want to do is I want to take this limit. And now we want to say, well, what if x goes to infinity instead of C? And we want to get to an L. Okay, so now we're going to let epsilon be greater than 0 because now we want to be near L, and epsilon tells you that how close to L you are, whereas delta tells you how close to C you are. So in this case, now we don't want delta to be greater than 0 anymore. Now we want n to be much greater than 0. And now we're going to let x be bigger than n. So instead of x minus c greater than less than delta, we're just going to say x is greater than n. So once you get past that value n, then you're close to epsilon. Any questions on that? And similarly, we can copy and paste this guy, and we can go to negative infinity, and not much changes. So now we want epsilon to be greater than 0, then there exists an n much less than 0. So now we want to go off to negative infinity, such that if x is less than n, then the absolute value of f of x minus L is less than epsilon. Have I lost you? So those are the definitions. Okay. Are there functions that don't have a limit as x goes to infinity or negative infinity? What do you think? Are there functions that don't have an L?
No.
One more guess?
Yes.
Yeah, and the answer is most. Not just yes, but most functions don't have a limit as x goes to infinity. I mean, you just throw a function out I don't know, y equals x squared. What happens when you go out to infinity for y equals x squared? If x goes to infinity, do you hit a number? What's infinity squared, or what's a billion squared? No, it just keeps getting bigger and bigger and bigger and bigger. Okay, so any polynomial of degree greater than 0, in other words, not constant, does not have a limit as x approaches infinity or negative infinity. All right, the graph either goes off way up or it goes way down. Does that make sense? Because you could do negative x squared and then you go negative infinity. Okay, in either direction. And you know that from just basic algebra, right? For it to go to a constant, an L, what does it have to look like if you just zoom out a whole lot? What does it have to look like? If you zoom out. The hint is it starts with an H. How does it look? Any thoughts? All right, let me give you some then, since you're not jumping in. So here's an example. How about x minus 2 over x minus 1? Now, if you look very far left or very far right, so let me zoom out. What's it look like? Kind of everything except real close to 0 in one word. What is it? Starts with an H.
Is it horizontal?
It's horizontal. So if you have a limit as x goes to infinity, or as x goes to negative infinity, you have a horizontal asymptote. Because if you zoom out and you just look far left or look far right, it's going to look horizontal. It's not perfectly horizontal, but in a limit, it's horizontal. Because if it's not horizontal, then it's not going to go to a y value. So here's an example of one that is not. Let's go back to how about sine of x? Does that have a horizontal asymptote? Does it have a limit as x goes to infinity? What do you think? Okay. Well, if we zoom out, is it looking horizontal? Not at all. It goes up and down and up and down and up and down and up and down and up and down. And I keep saying it, you'll just get tired. It doesn't flatten out. Is that clear? On the other hand, what if I did sine of x and I divide it by x? What do you think? Do you think that is going to have a limit as x goes to infinity? What do y'all think? If we divide by x. I'll do it, but I want you to guess first. I think that will have a limit as x goes to infinity or negative infinity. Okay, so yes, so let's see. Well, let's look left and right. Does it look like it goes horizontal? Absolutely. All of a sudden, it's just horizontal. Okay. So notice it still goes up and down, right? In fact, each of these points they're showing, that's where it crosses the x-axis. But the up and downness of it becomes flatter and flatter and flatter. Okay. So yes, it forever goes up and down, but that up and downness is flat. Okay, the up and downness is another way of saying the derivative, by the way. And the derivative goes off to 0. Okay, so that's going to happen. And if the derivative doesn't go off to 0, then you can't have a horizontal asymptote. You're not going to have a limit as you go to infinity. Any questions on that? Okay, and again, there's lots of these examples, but now let's do some without graphs. And I'm not going to do any example of proving anything with the epsilon n or delta n, because I won't test you on it. How's that? But you can be tested, by the way, in the final on epsilon delta. By the way, vertical asymptotes, when do they happen in the real world? Not as often, but they do happen. And it's usually bad or weird. Any ideas? May not even feel like the real world, but it is. Okay, black holes is a big example. So if you want to find out, if you want to find out how heavy you are, right? Believe it or not, you change weight as you go towards the black hole. Any guess on how much you're going to weigh when you hit that event horizon at the black hole? In some types of relativity, you're going to have an infinite weight. So you actually have a vertical asymptote. Okay. Similarly, there's all kinds of things where you get infinity. Okay. Another one is going the speed of light. That's another one you get an infinite mass if you decide to go the speed of light. Good luck, because you need infinite amount of energy to do it. So there's all kinds of infinities and weird stuff in physics. I'm not going to get into it though. Any questions at all so far? Okay, so now let's do some examples. So let's take a limit. So how about the limit as x goes to infinity? Of x squared minus 1 over 2x squared plus x minus 3. Okay, so we want to take that limit. And what you always want to try and do is plug in. If you plug in infinity, you get infinity over infinity, and that means we have more work to do. Okay, any questions on that so far? It's always the first step. All right, so the more work to do in this class is almost always algebra or trig. In this case, hopefully it's obvious it's not trig. So what algebra do I want to do to make this a little better? What algebra can I do? You could factor the numerator. It turns out that's not going to help at all. And I will let you know, factoring almost never helps unless you can factor an x out. So when you're taking a limit as x goes to infinity, and the reason why factoring almost never helps is that if we get x minus 1, x plus 1, but 1 and negative 1 are not important because we're going off to infinity. X is big, not near 1 and negative 1. So factoring the numerator actually doesn't help here. So let me tell you what you do. We divide numerator and denominator by the highest power of x. In this case, it's x squared. So, or in other words, I'm going to multiply by 1 over x squared on the numerator and the denominator. And you're always allowed to do that. And let's go ahead and do it. So that is going to be equal to, and let's just do that. Well, x squared over x squared is 1. So that x squared becomes a 1. And then we have a minus 1 over x squared. 2x squared over x squared is 2. And then we have plus 1 over x. And then minus 3 over x squared. Any questions on the algebra? Any questions? Okay, what do we do next? Now comes the easy part.
I'm gonna take a guess and say take the derivative, maybe.
That would be hard.
That would be hard, but
Let's not do it. No, this is easy, I
Okay.
promise. We've seen it with limits. I know it's been a long time since we've done limits, but we've seen it. What do you do after the algebra? Yeah, plug in. And it's very important to note that 1 over infinity is 0. And so is 1 over infinity squared, because that's still 1 over infinity. So everything is 0 except the 1 and the 2. We just get 1/2, right? 1 minus 0 over 2 plus 0 minus 0, which is just 1/2. Do you agree that's a lot easier than taking the derivative? Okay, just plugged in. 1 over infinity squared is 0. That was this part here. So that's just 1 minus 0 on the top, and that's 1. And 2 plus 0 minus 0, because 1 over infinity and 3 over infinity squared, those are both 0. So we just have 2 on the bottom. So you just get 1/2. Does that make sense? And that's it. Okay, it's not that hard as long as you know what to do. Okay, so what if we had, let's do another one. I'll just change it a little bit, but just enough that it changes everything. What if this x squared were an x cubed instead? How would that change things? What would you do on that first step now? Instead of multiplied by 1 over x squared divided by 1 over x squared, what would I multiply by now, top and bottom? Yeah, we're going to have 1 over x cubed over 1 over x cubed. And when I do that, things change a lot. So now we're going to have a 1 minus 1 over x cubed over 2 over x plus 1 over x squared minus 3 over x cubed. Now what happens when you plug in? What does the numerator become? One. What does the denominator become? 0. What's 1 divided by 0?
Undefined.
Yeah, so D and E does not exist. That changed everything. Okay, all I did is made that square a cube. What if I made this bottom square a cubed? Well, we're still going to multiply by 1 over x cubed, top and bottom. And now we get a 1 over x minus 1 over x cubed And then we get 2 plus 1 over x squared minus 3 over x cubed. Now what happens when we plug in? That became 1 over, not 2, 1 over x squared. Let's see, 1 over x. So what's going to happen now?
Zero.
Yeah, 0. We get 0 over, sorry, we get 0 over 2. 0 divided by 2 is 0. So that changed everything. So I want to let you know when you have rational functions, has a lot to do with which is the higher power polynomial, the numerator or the denominator. If they're the same, then you're going to get a nice number. It might be a fraction, but it's a nice number. If the numerator is a higher power than the denominator, you're always going to get D and E. And if the denominator is a higher power than the numerator, you always get 0. So those are really the only 3 cases there are. I can give you other examples, but they look like this. Any questions on that? Okay, just a note, if it's negative infinity instead of a positive infinity, let me just do this first one, because that's the one that really is interesting. The others don't matter. You get the same answer. So if x goes to negative infinity, then not much changes, does it? Do you get the same answer? What do you think? Is that correct? Okay, and the answer is, yeah, nothing really changed. Okay, nothing really changed. Still works. And if you change these infinities to negative infinities for the other 2 examples, you get the same answer. Turns out if you have a rational expression, that it makes no difference whether you're going to infinity or negative infinity, you always have symmetry. Got it? On the other hand, I want to do another example where everything changes and gets to be really messy, really weird. So let's do another example. Let's look at the numerator being x minus 1. And the denominator is the square root of 4x squared plus 1. All right, so we want to find this limit. The limit as x goes to infinity of x minus 1 over the square root of 4x squared minus 1. So to do that, we'll basically do the same thing. We look at the highest power. Now, what happens to a power when you take a square root? It's important to know. Yeah, divide by 2. So notice the highest power on the top is 1. The highest power on the bottom is also 1 because it's 2 divided by 2, which is 1. So that means I'm going to take what I had and I'm going to multiply it by 1 over x times 1 over x. One over x over 1 over x. Any questions on that? Okay, now I'm going to notice something very important. So note that x is equal to the square root of x squared. Do y'all agree? That as x goes to infinity, x is equal to the square root of x squared? Any questions on that? All right, well, because of that, what I can do is I can bring that 1 over x in as a 1 over x squared into the root. Any questions on that idea? Any questions? All right, so first thing, x over x is 1. And then negative 1 over x is negative 1 over x. And that's kind of dumb, but it is. And I can bring in an x squared into 1 over x squared in here. 4x squared over x squared is just 4. And then plus 1 over x squared. Any questions at all on this process so far? All right, what's the next step? What do I do now?
Plug in infinity.
Yeah, plug in infinity. 1 over infinity is 0. 1 over infinity squared is also 0. And I just get 1 over the square root of 4, which, by the way, coincidentally, I didn't mean this to happen. We have 1/2. By the way, not every limit's 1/2. I just maybe shouldn't have given you 2 examples that had the same answer. Any questions so far?
So for a square root, you always plug in 1 over x squared?
If it's a square root, if we have an x, then you make that a square root of 1 over x squared instead of a square, right? Because basically you note that x equals root x squared. Do you see that? So everywhere you see an x, you make it an x squared. Had this been a 1 over x cubed, then when we see an x, we put a x cubed 1 over x cubed squared, which would be 1 over x to the 6th. Does that make sense? Yeah. So this just this is an easier example because it's just x. But there's an issue. I'm going to copy and paste. And let's say instead of infinity, let's say we go to negative infinity instead. Is that correct? The way what I've now written. So I changed all the infinities to negative infinity. So the first step is to multiply by 1 over x on top and bottom. Am I allowed to do that? I noted that x is the square root of x squared. And then I put it in, I divided each of the terms by x, I divided each of these by x squared, and I get 1/2. Is that correct? Give you a minute, and this is important. Because we had. But if you don't think it's correct, where is the mistake? So I'll let you know from this last equal sign would be correct. Square root of negative. Not sure what you mean by that. Square root of x squared is the square root of positive. There's no problem. We're not taking the square root of a negative number anywhere. Okay, so I'm going to tell you this is not correct. But finding the error is hard. And it's right here. What's wrong with this? is it true that x equals the square root of x squared? Yeah, it's not or actually, it's negative. Because we're taking a limit as x goes to infinity, then by definition, x is negative. X is a high negative number. And if x is a high negative number, and you square it and take a square root, you're not back at x again. You're back at negative x. And that's why you have to write x equals negative the square root of x squared. So then what I'm going to do, I'm going to put in one more step because I think it's worth showing the extra step. If I can get that right here, let's just do this. Not sure if that'll work or not. So now 1 over x is 1 over x. There's no problem with that. But 1 over x is also 1 over negative the square root of x squared. Oops. Any questions on that? Because x is equal to negative the square root of x squared, it's not equal to the square root of x squared. And that's a subtle point where everyone makes a mistake. It's very easy to get fooled, but you can't just ignore it. Then we can take this negative sign and we can pull it out of the limit. And we don't get a half, we get negative a half. Any questions? That's my opinion. It is the hardest part of this day. Do you know what my definition of hard is? For calculus or for any math class? You know my definition? What do you think a good definition of hard is for a math class? When I say it, it'll make totally sense. That it's hard. That's not a definition. That's just repeating it. Should I tell you? Here's my definition of hard. It means that if I give it on a test, most people get it wrong. Isn't that a good definition of hard? Where easy, if I put it on the test, y'all get it right. That's my definition of hard. And maybe it doesn't, maybe you don't agree, but that's my definition. And this is hard because a lot of people blow it because it's subtle and very easy to not do and think you got it right, and then you didn't. So just note, if we have a square root and you want to put an x inside the square root, you can't put it as an x squared if we're going off to negative infinity. You have to have a negative outside. Got it? Could you do it positive and then add a negative? Not sure what you mean by that.
Like how you did the first one, and then since it's the same, is it always going to be the same?
No, that's why it gets really messy. Okay. Sometimes it is, and sometimes it isn't. And in fact, all kinds of things go wrong if this becomes a cube, for example, something like that. Things can go wrong. So no, you can't just take it negative at the end. That works sometimes and it doesn't work other times. So that's the bad news. Sometimes you get does not exist because you have a negative inside the square root and it doesn't work anymore. Does that make sense? So all kinds of things can go wrong. So you do have to do this note, and you have to note that x is negative the square root of x squared. Any questions on that? Had it been a cubed, everything changes because then x is going to be or let's say cube root instead of square root, then x will be negative the cube root of x squared. So all kinds of things go wrong, or x cubed, sorry. So x would be this cube root of x cubed if it's negative. So be careful is what I'm trying to tell you. All right, the last bit, there's not too much to say other than it's important to notice. What if I took the limit as x goes to infinity of the sine of 1 over x. Whoa, just lost it. Can we do that? Does that have a limit? What do you think? This is a transcendental function. Transcendental means it can't be written as powers of x. At least not a finite sum of powers of x. What's the limit as x goes to infinity of sine of 1 over x? The answer is pretty easy. That's a hint. There's not much to say. We're almost out of time, which means that we're okay because it's easy.
0?
Yeah, it's 0 because 1 over infinity is 0 and the sine of 0 is 0. So you still got to be able to do, limits, but that's an example of a limit. Any questions on that? What about the limit as x goes to infinity of the sine of x squared? What's that? That changes everything, by the way. Any ideas? The hint is it's easy. All right, if you don't want to tell me, it's D and E. And the reason is that, remember, by definition, if it existed, then it must be a number, right? So I'm going to tell you if it is a number, then it must be 0. And by the way, it also must be 1. Because if you threw a number at me, I'm going to be able to get a bigger number at which you get 0. Because I'll just take 2k pi, where k is large enough that it's bigger than whatever you threw at me. Or sorry, square root of 2k pi. And then square that, you get sine of 2k pi, and that's just 0. Okay, but I could also do 2k plus 1 over 2 pi. Take the square root of that, and then you'll always get 1. So it can't be both 0 and 1, so it doesn't exist. Because sine goes up and down, and up and down, and up and down, and it's not going to level off if you have sine of x squared. Any questions on that? Let's do one more quickie in the 1 minute left. How about the limit as x goes to infinity of, come on. The hardest part is typing these things. Not in. Of x times the sine. Oops. Let's just do it. X times the sine of 1 over x. Is that what I want? No, I do want 1 over x. All over x. I want that. Sorry. That's what happens when I'm in a hurry. I always have trouble. I do want x times sine of 1 over x. What is that? Okay, and here's the hint on this, the key. Take that x and rewrite it as 1 over x. Because that's x, right? It's tricky, but it works. So we're going to have a limit as x goes to infinity of the sine of 1 over x over 1 over x. Okay, now the idea is, what does this become? And the key is, if you let u equal 1 over x, then what this becomes is, well, if u is 1 over x and x goes to infinity, what does u go to? Zero. And similarly, sine of 1 over infinity is the same as the sine of u. And 1 over x is u. And now you should all know this one by heart. What do you get? This one you're supposed to have memorized. Yeah, that's 1. And that's my last example. But you can do lots of sines and cosines and all kinds of stuff. And I gave you a few. So let me stop. I'm a couple minutes over. Sorry about that.